We can use the steady state approximation method to determine the rate law for a multi-step reaction where the rate determining step is not known. So first we'll assign a rate constant in the forward and backward reaction of step 1, and another rate constant for the irreversible reaction in step 2. And we'll write the rate law using the irreversible step. And because B is an intermediate, it's being produced and consumed in the elementary steps. This is not our final rate law, which we need to write in terms of the reactants. So using the steady state approximation, where the rate of change in concentration of B with respect to time is 0, or the rate at which B is consumed is equal to the rate at which it's produced. So in step 1, we can write the rate law for the forward reaction as follows. And in the backward reaction, B is being consumed, so we subtract K1B by the concentration of B. And in the second step, B is being consumed, so we'll write K2 by the concentration of B. And then if you do some algebra, you can solve for the concentration of B. And now we can substitute for the concentration of B in the rate law. So this here is a constant. So therefore we can write our final rate law as follows, which is second order with respect to reactant A. The pre-equilibrium approximation can be used to determine the rate law for a reaction mechanism where the first step is an equilibrium reaction and not the rate determining step. So first we assign rate constants for the forward and backward reaction and the irreversible reaction. And now we can write the rate law using the slow step. And B is an intermediate, so this is not our final rate law, which we need to write in terms of the reactants. So using the pre-equilibrium approximation, we assume that equilibrium is reached quite quickly, where the rate at which A is consumed in the forward reaction is equal to the rate at which B is consumed in the backward reaction. And now solving for the concentration of B, and substituting this in our rate law, we obtain the following expression. And this here is just another constant. So we can write our final rate law for this reaction mechanism as follows, which is the same result that we got using the steady state approximation.